In the previous session we were talking a bit about the idea of the measurement problem and the idea of collapse of the wave function. That term gets used a lot in quantum mechanics. So in the context of the thought experiment from a couple of sessions back on the box with trapdoors, n minus one of them, so the trapdoors fall and the particle is in one of those volumes, so the n, big N volumes, and then say you observe that the particle is, let's say it's in volume little n. It's in the nth volume, let's say. So that means that the wave function in all the other volumes suddenly becomes zero, right? So they in a sense collapse. So your superposed wave function, your psi, then collapses to just psi of n, because now you know that the wave function, that the particle is in volume little n. Now what's the probability? Before the measurement, before you do the measurement, your wave function is the superposition of these waveforms, psi of m. And I'm not quite sure. I'm not quite. I think you can probably actually see this in the frame of the camera. So your general waveform is of the form sigma Cn psi of n. Okay, so that the probability of finding the particle in the little nth compartment or volume is in fact Cn squared, right? And that Cn is the coefficient. You see in here, it's the component of psi of n. Looking on psi n as a vector now. Okay. So that means that if your superposed, general psi function, just psi, if it's in n-dimensional space, vector space, if that is almost parallel to one of these other psi, let's say psi n, so if psi, the superposed form, if it's almost in the same direction, parallel, quasi-parallel to psi of n, then a measurement of the position of the particle will give a high probability that that particle is found in the volume n that corresponds to that wave function. Now, correspondingly, if your superposed wave function psi is pretty well orthogonal to psi, well, say psi of k, or psi of n, doesn't matter. We'll say then orthogonal, what does that mean again? It means the overlap integral is zero. So if you have two functions, psi m and psi n, then the overlap integral of those two will be zero if those two functions, wave functions, or vectors, are orthogonal, by definition. Right? So if this is pretty well orthogonal to this function, so if you take the overlap integral of this and this, you'll get zero. So that means that the probability of finding your particle in this volume corresponds to this wave function is pretty well zero, right? Okay, so generalizing these two ideas, high probability, low probability. So if the overlap integral, the bracket, if you like, several ways of talking about this. So if the overlap integral of two functions, psi and psi k, is large, then the probability is high of finding the particle in the volume corresponding to this wave function. Okay. Now, if the overlap integral, or the bracket, of these two functions is low, small, then the probability is low of finding the particle in that volume corresponding to this wave function. This is the wave function I assume. That's why I was feeling rather antsy, frustrated in the first section of this lecture. And just what this is. I assume it takes non-zero values in volume, the kth volume, and is zero elsewhere. That's my interpretation of what Davies was trying to say. But my feeling is he did not express himself clearly. Okay. All right. Now let's say now we're talking after the measurement. You've actually looked at where the particle is. You've found it to be in the kth volume. So you know the wave function now has collapsed from the superposed state to the state where the psi k. So we know the particle is now in the kth volume. So that means that in all the coefficients, all the components C, the complex numbers, corresponding to non-k, all these CNs where n is not equal to k, all those components suddenly become zero because you've made the measurement. You now know the result. Okay, and so the only non-zero C will be when n is k. Right? So that means now. So once you know the particle is in that kth volume, if you do a measurement, your your wave function is now this, then with certainty, so ck will be squared, will just be 1, probability is 1, that means certainty, right? That you will find the particle in the kth volume because it was there to start with. You knew it was there, so you're just confirming that it's there in effect. So in other words, your psi k just remains unchanged. It just you do not get another collapse of the wave function because it was psi k to start with because you knew the particle was in that kth volume. Now this leads. You're probably getting a stronger and stronger sense for the nature of quantum mechanics in the sense that its interpretation is not obvious. That's one of the points I'm really trying to drive home in this whole lecture course, this lecture set, is that the interpretation is there's no consensus, and the formalism there is. Like quantum mechanics is obviously doing something right because it's so spectacularly successful and accurate in so many cases. So I make an analogy with quantum mechanics and China. Remember, I live in China, and Chinese medicine. Empirically, I just know from my own experience, some Chinese medicines work well. I mean, I've tried stuff. Some of it works really well, and better than the Western medicines I've tried for certain things. So empirically, in terms of actual experience, there are certain aspects of Chinese medicine that work really well. So you keep those. But when I look at the theory of Chinese medicine, with its qi and all that kind of stuff, well, to be frank, in terms of modern scientific knowledge, it's just garbage. Right? It's just bullshit. But empirically, the Chinese doctors, so-called, are doing something right, because based on experience they've found empirically that certain remedies and whatnot work, they actually work. Well, you see the analogy, I suppose, with quantum mechanics. The formalism works. It's predicting results that are very well confirmed in the lab, so in that sense you keep that. But the theory, I mean, the interpretation, what are these wave functions? What's going on? That's much more dubious. And in some ways, if I are alive a century from now, I'd be very curious to see how humanity, or post-humanity, or our intelligent machines who supersede us, how they will look upon quantum mechanics. How will they interpret quantum mechanics? Because for me, just one big question mark. All right. Okay. So we're talking a bit about the collapse. Now, this vector language, because we've been translating wave function type thinking, wave function language, into vector language using techniques from vector space theory, from mathematics, pure math, and finding it very convenient to translate the wave function way of thinking into vectors, right? So, but it's just a rewriting technique. There's no new physics. But when we start generalizing, we're talking about measurement of position, effectively. You know, is the electron here or here? Or, yeah. But the ideas that we've been developing now, we can take over for other